All right, so let's see here. So we're getting into, let's see, the past few things we've done have been neural networks, right? And seeing how we can apply for neural networks. A lot of times these are also referenced as multi-layer perceptrons or MLPs. And basically you can think of it as kind of like the basic form of neural networks is like one perceptron, right? And then we build the perceptrons on top of it to make a neural network. And we put multiple layers to basically make deep learning, right? So that's what we've really been doing is deep learning. So there's other things we can do too, other architectures, and one such thing is a convolutional neural net. And that's actually what we're going to talk about today and introduce. So, but before we go into like a convolutional neural net, it's kind of important to understand like what neural networks in the form that we've learned already, MLPs, what they can do really well, and why we would need a different architecture to do something. So one quick thing, I'm just kind of go over like where convolutional neural networks are actually really decent at. They're basically good at, they're used a lot in like image recognition, and we'll see why that is, but basically it comes down to like finding patterns that are kind of localized together, and we'll talk more. But first thing I want to share is, I'll go ahead and start sharing my screen right here. And we'll make this a little bit bigger so I can actually cover everything. Okay, why does my windows always move? Okay, so the first thing we're going to talk about, since we're going to focus mostly on convolutional neural nets for object detection, sorry, not object detection, but also image recognition. That's what we'll focus on today. It's important to understand like how a computer sees and what this actually means. So just know that computer basically just has an image. If it's a grayscale image, it's essentially a 2D object. So you can think of like a grid of numbers. So if I were to kind of like, quickly just kind of draw this out, you can imagine if I had a grid right here and each pixel color, or basically each pixel represents how bright they should be. 0 meaning that it's like black, for example, and then let's say up to 256 bit color. 255 means pure black, okay, or at least as dark as possible, okay. So images are just really a bunch of a matrix of values. Note that for a grayscaled image, it's just one 2D like 2D tensor, 2D matrix of numbers. If we had colored images, right, we actually have a multi-dimensional color. So for example, if this represents the red pixel, we would have maybe like another layer of numbers to say how bright the blue pixels would be, okay? And then we'd also have something like, oh, how bright should the green pixels be? We also can have things like alpha and like gamma and other things. So you can actually have 4D layers and stuff like that. But the point is essentially we have like a tensor of numbers. It's really what images are represented within computers. And this is what actually, like how digital cameras work. Basically just saying, hey, like how bright is this pixel? Okay, and that's how we kind of go through. So that's really what a computer sees. And that's an important aspect right here, because one thing to note is that like we see it kind of like all together, but a computer can only read one at a time. So we'll find out that this structure that the images are made into doesn't really work out for neural networks because we have to convert them into a different kind of format. So one thing you'll find out is that neural networks are not very good. They're not very good at image recognition. They can be in certain situations, but it comes down to a couple reasons why. So the first reason why is that we need to feed a vector into a neural network. So remember back in our neural networks when we learned about them, the neural networks basically just have these nodes right here, this input nodes, right? And then those would get passed into, let's say like into our different parts of the network like this, right? Our different nodes right here. And this is the stuff that gets trained. So the problem is that this right here is just a vector by itself. So we can actually do this for like if we have a 2D image like this, right? We have a 2D grid. Let's say it's grayscale just to make it really nice and easy. And we have a bunch of numbers, right? So let's say, we have 0. I'm just going to label 0, 1, 2, 3. Okay. So like we have these next parts and let's say this is like 10, 11, 12, 13. The problem is that we can't just take this 2D matrix and feed it into our network. We're going to have to actually split it up. So like if I had this 2D network, we can do something called flattening the vector. And essentially what that does essentially takes this first row right here and says, okay, here's all that stuff, takes the second row, all of this stuff and makes one big vector. So this would, for example, be like 0, 1, 2, 3, and this would be like 10, 11, 12, 13. And then we can feed this whole vector into our neural net right there. Okay, so the problem with this is that we lose spatial information. And what is spatial information? Like, what am I actually talking about? So whenever you look at like your image, so let's say we have our image, we'll just use 4 little dots. Okay. Or I'll make it more. So we have our image like this. The problem is that when we have an image, let's say I'm just going to draw a very simple happy face. I can actually, let's see here. Or maybe I'll just draw a circle. Okay, so it's dot here, here, and here. Okay, so this like makes more or less a circle, right? So it's important for us to understand, like, okay, like, well, this right here and this pixel, these are connected in some like spatial information. But the problem is if I actually split this out, what that will look like, right? It's like, okay, well, I have to flatten out the vector. Okay, and I'll just kind of make it really quickly. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5. 1, 2. I think it's just enough, whatever. Okay, I have to flatten all out. And what happens is that this pixel right here is going to be colored in right here. And then we skip over 2. Oops. This color gets colored here. This gets colored here. And then 2 over gets colored here. And the problem is that this right here might not be easily recognizable as this is a pattern that's structured around here. And if we have like, you know, if you imagine this big old grid and we had a picture of, let's say, like a little person here, right? Well, the problem is that it's important to actually recognize that these parts of the image should be connected together. This is really the one object. But because the computer basically will only take one line at a time like this, it's going to split up that image and it's not going to make as much sense when we pass it through the neural network. So we lose this spatial information. Now it turns out for very small images, like relatively small images, we can actually do a decent enough job. But as we get more and more complex, it basically ends up being really, really bad at detecting this extra spatial information. Also, think of it this way too. This network, for example, you can see like, if I have a person like here, this would basically say, okay, you can find that pattern. But imagine if the person's like really small, like someone's in the distance. Or if someone's like, you know, let's say sideways or off the left, right corner, it's not really clear from basically getting all those pixels parts. They're not really kept together. So they're gonna get spread out as we're basically designing or making our vector to feed into our traditional MLP neural network, okay? So just to kind of show you how you could do this though, I do have a demo of an MLP stuff, but I actually, I found that my computer wasn't doing too well doing it, so I'm actually put in Google Colab here, but it's in the same notebook, so it's kind of, so same stuff we have here. And the first thing to show you is, let's just make this small so I can, okay. So the first thing we're gonna use the MINST, what's it called? Database, and the MINST is basically just some handwritten digits. I think it's 28 by 28 pixels. So if you look at this, this is like the different images right here. So for example, this is number 5, this is number 0, this is number 4. It basically goes through 0 through 9. And you can see here, they have the labels going on. So this is actually a really great data set to test things out. I believe it's 28 by 28 and it's grayscale images. You'll notice that they look kind of blurry, and that's mostly because we just zoomed out on it. But we could, for example, if you saw in the little picture, you would probably recognize it as 5s and 4. And they all have basically people who humanly drew different numbers and stuff like that. And for the most part, they're mostly centered. They take up the whole space of this image. So they're actually a really good candidate to be able to use for neural networks. But here's just kind of show you like how you can do this. So the first thing you do is I'm just showing you the information. We already loaded the data set. Turns out this data set from Keras actually has X-train and Y-train and X-test and Y-test for us. So we can basically just load the data and just do this directly, okay? Which makes it really consistent. So we can basically, one thing I'm gonna do though, is that because each pixel goes from 0 to 255, I'm gonna normalize it to basically go down to 0 and 1. So that way our neural network doesn't take a long time and large values like we talked about last time, how we can optimize it for basically through normalization. So that's why I'm doing this guy right here, okay? So we can rescale each image, and then I'll also one-hot encode as we typically do for categories, right? for classification. So basically this is taking the stuff like the labels themselves, either it's the Y training labels or the Y testing labels, and just making it into a categorical variable. So I know which variable is supposed to be what, or which class is supposed to be under what, right? So this right here, this shouldn't be new too much. It's the same stuff we've been doing for basically implementing in Keras, right? We can see here I basically have a sequential model, so it's going to be an MLP model. We're going to basically flatten out the input. This is relatively new, where we basically take something that's 2D, and we're going to basically take each row of the data and make that and stitch it together to make it one vector. So that's called flatten. So you can see here, basically, I'm going to flatten out this whole input right here for X train, okay? And I'm using the same dimension here. So I go to that, and then I have two different hidden layers. In this case, I just started with 16 nodes. Why 16? I did it just because I think the 3 blue, 1 brown video does this, like actually uses this data set and uses 16 just to kind of like, all right, we'll use 16 just because. I also have this dropout layer, right? I did about 20%. It's a 20% chance that each node will drop out during each epoch. So you can see I can basically train the model over some time. And then I also have a classification layer, which is our final layer, which is our dense layer, right? Just a bunch of nodes. It's 10 different nodes, one for each of the different digits it can output. Okay. Any questions on this?
One quick question, and I think it's kind of dumb. You're adding the layer named like hidden layer 2 or hidden layer 1, and then the dropout kind of code, it knows what layer, like how does it, does it have to be in that sequence, or how does it know specifically that?
That's right. It's basically, you can think of like when you're doing this model.add, we're basically saying we're stacking the model, like the stuff on top of each other. So it knows that, oh, the dropout is applying to this specific layer, and this dropout is applying to this specific layer. For example, if I did something like 0.1, okay, it would be 0.1 would be for this layer specifically.
Okay, so it's just like in a sequence.
Yeah, in different libraries, they might do this differently, but the idea there, for example, I'm trying to remember if Keras, you can actually define, maybe not, but some models you can actually define the dropout directly within declaring the layer itself. So instead of having this add dropout, you would actually have it within here itself. Okay. Yeah, cool. Good question though. Yeah, you can think of like the dropout layer as not really a layer. It's much more like part of this first one. Okay, so I have my structure here, and it's nice that we do a model.summary so you can actually see all the different parameters. So we can see here, we have a 784, which is basically 28 times 28, basically how many pixels we have. So basically each pixel is going to be an input part of our vector. Then we have 16 different, 16 different nodes here. And you can see the different parameters that we have essentially. And then at the end here, our dense layer, basically how much will come out from there. So you can see here is that we actually have quite a lot of parameters, 13,000. But this is only for a 28 by 28 picture. This is one of the other reasons why MLPs are pretty bad at actually doing image recognition. If you had anything that's like relatively like decent quality image, you would have a ridiculous amount of parameters. And that's not even including all the different hidden layers you probably would have to include. So this is one of the reasons why neural networks can't work out. But this is a pretty good candidate. 13,000 parameters is not too bad. Okay. So we're also going to basically compile our model now so we can actually use it. So remember, we're using categorical cross entropy as its loss. In this case, I'm using an optimizer, Atom, right? And this too, what's nice is that it'll actually record the metric to accuracy for us. So this is something that's nice for Keras. So we go to compile this, and now we're actually going to go ahead and run it. So this is actually a really useful thing that I hadn't shown yet. So this right here is your model checkpoint. So this is kind of similar to like when you do like early stopping, where you want to basically get the best model that worked out well, or you want to get a specific one. You can actually save the models right here, usually called a checkpoint, right? And so basically this model checkpoint function right here, or I should say method, will actually save the model into this file. And usually we do .hdf5 as the format. So that's the extent that you'll tend to see. And then we'll basically, we'll only save the best one. So this is actually a really cool thing that you can look more into. But the idea here is that we'll basically do multiple models as each epoch, and we just want to save the best one that worked out well, okay? And then we're just going to go ahead and basically do the model fit. You can see here, we're going to use a batch size of 128. Because remember, we have, actually, I don't think I showed how many points there are. I believe it's something around like 16,000. I can't remember now. But we're only going to use 128 each time for each epoch. And I'm actually going to drop it to 8 epochs just to make it pretty quick. And you'll see this will go by really quickly because there's only 16 layers. So you can see here each epoch's being trained, and you can see here also there's the accuracy, the value loss, and validation loss, and the validation accuracy. And you can see the final accuracy here. And you can see here is that every time it does better on this epoch, it will actually save the model. And then I think each time in this case, we actually get a better model. But if it wasn't, it wouldn't actually save it. And at the very end, it looks like we got about this validation accuracy is about 0.93. Okay, and you can see it improved each time. So if we run this now, we'll actually see our best model, and our best model had an accuracy on the test about 93%. Not too bad. Okay, we could improve this. One way we could improve this really quickly is just putting in, for example, let's say, just train it more times. So you can see each epoch takes only 2 seconds. So it's not, or in this case, almost 1 second, right? And you can see here, like this example, we actually didn't get any better on the validation loss right here. You can see that it didn't improve, but in some cases it does improve. So we just keep saving that model, and you can see on the side here, this validation accuracy is increasing. And hopefully at the very end of it, we'd actually get a better model. So we'll check this out in a second. Another way we could have done this too is to make it more complicated, right? It's basically just put this as more. So for example, I could have been like 64 and let's say 64. Okay. It doesn't have to be the same. I could have done something like, let's just actually try that out. Let's try like 128 and then 64. And you can kind of think this is it trying to find the different features from the density, from the inputs here. So I'll run this in a second, but let's check out how our model did. It's probably done. Cool. And so we can see here, we basically got essentially the same thing, a little over 93%. So it's getting, like, I think we could probably do a little bit better. So I'm going to try this. In this case, I'm going to change it down to just 8 epochs, so we don't have to run it forever. These can run for very, very long time. So you see, I have new model, and you can see here now we have a lot more complexity, right? It's about over 100,000, right? We'll now compile it, so now we have this new model, and now we'll go ahead and train it, and we'll still do a batch of 128, but we'll keep the epochs to 8. And you'll see that because this model is much more complex, you can see it takes a lot longer for this each epoch to actually execute through. And you can see here though, already within like 2 tries, we already got a higher validation accuracy than we had before. I think the highest one we had previously was like 94%. So this is kind of like how you kind of do some quick things to like basically adjust your model and going through. Usually your epochs will take a lot longer if your model is really complicated. So you can see here, we ended right here, and it looks like almost every time, except for this one right here, we actually improved our model each time. So now we can check out our accuracy. Remember, we had about almost 94% accuracy for the test. And we can see we have about 97% accuracy. So you can see here, like we can adjust this and tune it a little bit better. For example, we might, make this more complicated, maybe do like 256 and 256 or 128, maybe add even another extra hidden layer if we wanted to. We could basically adjust our dropouts. We can do a different optimizer. So you can basically keep playing around with this. But again, 97%, that's pretty good. And again, the only reason why this will work really well is because we actually have data that works well for an MLP. So the thing is though, if we get more complicated images besides just a simple 28 by 28 image where it's all centered in here, takes up the whole box, this is when we'd start running into issues, and it'd be near impossible to use just a vanilla MLP to actually train this image. Okay. So any questions on this completeness neural network?
No, I think I got it.
Okay, cool. Yeah, so this is probably like, this is basically all the stuff we've already learned before. So now we're actually going to see is how to introduce this with a CNN. So like I mentioned, CNNs, what are they used for? Like, what are they good for? It's usually associated a lot with like image recognition, but CNNs aren't just like for images or computer vision. It's also useful to find like speech patterns. I believe it's even been used to like help develop, I think AlphaGo used it, a CNN. And basically the way I kind of think of it is that you're looking for patterns that are closely bundled together. So for example, in images, you have spatial spatial patterns, like patterns, like for example, like in this painting, for example, you can look for, there's a circle right here that's grouped together. It's not an individual like pixel or pixels in sequence, right? Like this right here, finding this objects that edges and stuff like that. You're basically trying to find these patterns that are closely bundled together in some way. And this is why speech pattern is good for speech, for example, is that speech really matters, like the way the sounds that you're producing. It's not about like just what individual sound is produced throughout a whole like sentence. It's about the sounds that are produced close together. And this allows you basically to create a hierarchy of patterns. So like essentially you could say, oh, there's this pattern here, and then we'll actually build more and more. So for example, a simple pattern might be at first like just finding edges and saying, you know, where are the edges that exist? And that's not really going to help you to figure out, for example, is the picture a dog or a cat, but it'll help you basically determine, what's it called? Determine like where those edges are and stuff like that. And then you can start building more and more complex features. So we'll see what the goal is for our CNN. Basically, will basically to take something that has a lot of spatial information and convert it down into almost no spatial information, which basically is just saying, oh, are there whiskers in it? Are there ears in it? Are there eyes in it? And then build out, say, from those features, from those really complex features, what is actually in the image, okay? So it's kind of similar to our neural networks in the sense that we have multiple multiple layers. We can actually use the same optimizers, which is awesome. We can use the same loss functions. It's, like I said, it's a layered network that we have different structure architectures. So we can see here, for example, this 28 by 28 image, just like we saw in our example over here, right? Same thing. So what happens here is that we're going to introduce some new architecture, for example, convolutional layers. And basically this will create features from the images, and we can basically have many different like filters, we'll call them, different convolutions to essentially create new features. And then what we'll do is something called max pooling, which essentially will downsample our convolutions, okay? And basically then we might do another convolution, which basically finds patterns within patterns. So we have our patterns and seeing what other patterns within those patterns, and we'll do more downsampling. And then eventually at the very end of it, we'll actually have this nice set of features that is going through, and we'll actually feed this into now an MLP, a fully connected neural network. So, and then once we have these nice features, for example, like you can think of it like, oh, are there whiskers in it? Are there, you know, eyes in it? Are there ears in it? Is the color brown? Like these more advanced features, we'll actually feed this through our neural network, and it produces our classes here, okay? For the image like detection, for this like number 2, number 4, number 5, you can think of it saying, oh, is there a swirl? Like, is it a straight line? Those would be like the more complex features that we'll use for a convolution and be trained onto a neural network. Okay, and this is because of this neural network right here. This is some of the reasons why we can actually use those optimizers and use the same loss function. Essentially, because at the very end, you just stick on a neural network or MLP and train it from there. Okay, but I would say like overall, what you should think of like CNN, what it's doing is basically taking something with a lot of spatial information and converting it down to basically something that's like almost no spatial information. And one way you can kind of just think of this is that we're taking something with a lot of like pixel density information that's very like, how do I say this? I almost say like blocky, like a lot of like extra information, and we're basically stretching it out to basically say, okay, does it have this? Does it have this? So you can kind of see this dimensionality reduction right here. So you can see we start off by a 24 by 24 by, and this is N1. Basically like we have this very large blocky kind of thing, and we basically keep reducing it until we get down to something that's a lot, what's it called? Like I think of it like a lot skinnier. Basically the features are very complex, so they hold a lot of information. Like when I say, is there an ear in it? Well, that's a lot of complex information about like visually, like what is an ear? And that's the stuff that basically is being found within these convolution layers. Okay, cool. So that's gonna be our introduction to CNNs, and we'll actually see what the parts of the CNN are. But any questions from just generally connection from this to neural networks?
No, I think I got it.
Okay, cool. So I will show you now the parts of a CNN. Okay, So let me go ahead and minimize this stuff so we don't have it be distracted by all those things. Okay, so like I said, this is another image right here that I just found on the net. Basically, is that we're taking an input image right here, and you can see here they even have like 3 slots. Like if it was colored images versus a grayscale, we actually have 3-dimensional input, right? And so we take this, basically we'll do a convolutional layer right here, and we'll take this part in here and basically get certain patterns in there, and we'll build this new kind of like block of features, and eventually we'll basically keep doing that. In this case, it's downsampling, more convolutions, and then finally until we get basically something that's feature rich, Laura mentioned, and we'll convert that into a vector with flattening, and then we'll do a fully connected, and we'll actually be able to tell different classes from there. Okay, so the first, basically the main things you need to know is that every convolutional, like a CNN, as convolutional neural net, basically is built on 3 parts for the most part. Is the convolution layers, the pooling layers, and a fully connected layers. So you can see here, for example, this feature learning aspect basically is trying to learn all these different features. This contains our convolutions and our pooling layers. And then at the very end, when we actually do the classification, that is our fully connected layer. Okay, so that's kind of like the way you can kind of build things up. And that's really the only 3 parts of the whole thing. It's just about how we go about it. So the first part is the convolutional layers itself. So this is the stuff that's probably the newest things. And basically you can imagine having this special window right here and dragging it across the image. And basically you drag this window, and essentially it's a filter, and basically summarizes each point going in there. So you can imagine like, this I think came from Stanford's summary, like cheat sheet note for their course. But basically you can see this image, you have this window right here, and it's being dragged across the image. And then as we drag across each image, each time it gets dragged off, it basically summarizes as a single point, essentially as a single number, is what we're gonna see. And that can help us basically find extra patterns depending on how the filter is created. So one thing we have to kind of consider is basically when we're actually creating this convolution is basically how will the window determine the patterns? Basically, this is the filter. How is this constructed? And then also, how do we drag the window across the image? This will talk about stride and padding. So I'm actually going to show you from another website here. This is what I was saying. I can't read it from here. Stanford's CS 230 course. So this, I think this is free online too, that you could actually take this course. At least watch the whole thing. It's recorded. But anyway, there's the image right there. And you can see here, basically we're making these convolutions of these different filters going through. Okay, so I think actually I have it right here. No. Okay, good. I didn't think I had to fill those out. Okay, so you can see here the very first part is basically this filter is basically just being dragged across. And this filter is really built out of numbers. And we'll show that in a second. But these different filters, basically, you can construct them with different numbers, and this will multiply each part in that number. So if I took like any one specific, I don't know if I can actually do this. Okay, well, I can't do it well. But if I imagine dragging this window across these 6 elements, this might have, for example, basically multiplied by 1, multiplied by 3, multiplied by -1. And basically those numbers will be added together and will be converted into this part. Usually this filter, after you do kind of like summation, you would do like a ReLU. And basically this thing summarizes a whole number set into one data point. Okay. Next part, let's see here. Actually, is this what I wanted to show you? Oh, yes. Okay. So then for our extra filter, we have something called stride and padding. So stride basically just says, how quickly are you dragging it across the window? So do you go one step each time? Like in this example, we basically drag it across 1 each time going through, or do you drag it over twice as fast? So if you drag it over twice as fast, for example, you skip over each one, you actually reduce the dimension of it each time. So this is something that can be used to basically essentially kind of downsample, but also find like more larger features versus very fine-tuned features. So stride usually, sometimes it's set to 1, sometimes it can be set up to a higher thing, like up to 4, basically saying how many pixels do we skip over to go across the whole image. The next part is the padding, and you can see here basically different kinds of paddings. For example, there's the valid, which is basically just saying no padding. And so one of the reasons why we do padding is because we might want to make sure that we actually cross over each part of the the image. So if you look carefully, I think this one's a better example. As you can see here is that when we go across, we actually run across this one, let's say like this middle pixel, this will hit 3 times each time we go through. So this middle pixel will actually, each time we go through, will actually be counted 3 times. But if you look at this top right one here, this gets only hit once of that whole pass through. So it basically means that this stuff in the middle is more important. So what we might do is actually add in padding on the side over here, and that way it has more chances. So you can see here, it'll have more chances to actually get moved across. So that way the stuff on the border isn't the most, isn't less important than the stuff in the middle. So this is one strategy. Valid basically means you don't do any padding. And then also same just means that you basically add extra padding on the side here. So it does have that extra, basically getting those extra edges. And you can see basically, you can see the full padding over here, and you can define these patterns. And this is all dependent on the library. Okay, so those are stride and padding. And then the filter, I'm going to kind of show you an interactive example of this. So this is a great website here. Basically, this person has made a bunch of different visualizations for this stuff. And so he kind of shows you, for example, like each of these pixels, like you can see this very small picture right here, it's blown up here. And you can basically say each part of that, the image, for example, that on the red square on the right shows a number off to the left here, okay? So you can just showing us, oh, it's just a bunch of pixels. And what's kind of cool now is that we can actually, this is a filter right here. So this is like I showed you, like literally this thing right here. What this is basically just saying what the numbers are. So 0, -1, 0. And basically you take each number in this little box. So if I take this little box right here, my little filter, and I drag this across, each of those boxes basically is a number times that number right here. And then we add it all together, and that will give us a number, and we'll actually pass that usually like through like a ReLU. Okay, but you can see here, for example, if I have this value here, most of the values are very, very large, right? And so its total value is 256, but if I drag it over to something like this, you can see the values are closer to 0. So you can see here, as I drag it across, we can get different numbers. And on the right, the far right, the output image is basically taking that 92, for example, and pushing it out off to the side here. Okay, cool. So what we're going to do here, so one thing you can do, you can see, for example, this is sharpen. This is to find the outline, and you can see the image on the right here and the way it changes out these numbers, for example. Okay, so you can see, play around with this. This website's really great to actually get an idea of like what it's doing and like what different convolutions are doing. You can also define, this is kind of cool that he built this. You can upload your own image on here, but also change out the different values. So for example, if I do a custom, I can possibly do something like, change these values and actually looking for different parts and different patterns and see what that looks like. So this is a great kind of thing, but this is the filter right here, is this decides on what kind of filter to do. And you can see that there's a lot of different possibilities, but essentially we'll drag the filter all the way across, right? And we'll produce this right here as a new, basically, image. So we might have multiple filters for our one image, and this will create basically a layer of different, like a bunch of layers of these different filters, different images that we can now train, well, we can go to the next step from. Okay, so any questions on that part for the convolutional networks? We have the filters, the stride, the padding.
Yeah, no, I think I got it.
Okay, cool. Cool. So that's our convolutional layer. And the next part is the pooling layers. And basically there's 2 types of pooling. There's max pooling and average pooling that we tend to do. Basically, all you can think of this one is essentially, if I were just to look at this, like my little square right here, basically it takes our thing on the right, so this guy right here, okay, and it'll actually take this guy and go ahead and, what's it called? We'll sample, basically try to summarize this part. So for example, doing the max pooling, if I had this guy right here, so I'll just kind of go across, it'll look on that, this guy right here. So look at this right here, and we'll look for what is the maximum value in here. And we'll actually just record that one number and make that image. So basically, it effectively will reduce the size of that layer. And you can see from this part, for example, I think there's a pooling section right here. You can see max pooling and average pooling. So you can see here, basically, it's the same idea where you drag a filter across, and this filter will basically summarize into a single number and basically downsample, make it smaller. So that's something to just kind of just know what it will do, kind of like sorry, we're basically trying to summarize. We're just trying to get rid of the spatial information. We're trying to get it as small as possible so we can actually find the deeper pattern. We don't really care about specifics of the pixels. We just care about the patterns themselves. Okay, and so we can actually repeat these process over and over again. So as I kind of showed right here, is you can have a convolution, then a pooling, and then a convolution, then a pooling. And basically that allows you to find the patterns within patterns. So you can imagine, like on this guy, we would take something like this and a bunch of other images and move it into, basically find these patterns within patterns going forward. Okay. So yeah, so that's our max pooling, and then how we would combine these max pooling in convolution layers together over and over and over again, and then use a fully connected layer at the very end, which I don't have to go into because we talked about. But it's basically you have this part, you flatten it out, and you basically do your classification on top of here. And that essentially is a convolutional neural net, which sounds really like oh, not too bad. But what it comes down to, sorry, hold on. Hey, come here. Sorry, it's my dog. Hold on a second. I'm just gonna hold it for a second. But essentially that concludes our convolutional network. Yeah, any questions?
Yeah, no, it seems like there's a lot of parts, but they're all simple enough.
Yeah. Yeah, that's the thing. Like I feel like a lot of the times with the neural networks, it's not about understanding the specific parts. It's more like figuring out like what works well, mixing it together and everything. Sorry, I'm holding my puppy because she.
Thank you, puppy.
Oh, thank you.
Every time I heard her, I assumed she was a lot bigger.
I know, right? Well, I do have another dog. This is my second dog, but I'm on puppy duty right now for the next like half hour. I'm sorry, you were muted. I couldn't hear you.
Oh, very understandable.
Yeah. So she wants to go play. I'm like, all right, just give me a second so I can let you out. And okay. But yeah, the convolutional layers and everything like that. It's not so much about what specific one. It's all about architecture. So we'll kind of talk about that next time too. I think, but basically they're like different things that worked really well. For example, AlexNet and stuff like this, and different layers of convolution. What kind of how many convolutions you use, what kind of filters do you use. That's the part that's kind of the testing out and everything going forward. Okay.
Okay.
Cool. So I'll go ahead and stop recording since I think that's all.
I can't hear you.